Hello dear students, I welcome you all to online lecture series, an initiative by Progressive Education Societies, Modern College of Pharmacy, Pune. Students, today we are going to discuss about a new topic, that is gaseous state. I am Dr. Smita Pimple, Professor, P Societies, Modern College of Pharmacy, Pune. In previous video, we have discussed about the transition of states of matter, like how the gaseous state, liquid state and solid states, they converts into one another by means of changes in surrounding conditions, and this transition is related with the degree of intermolecular forces of attraction which are present. So solids, if supplied with energy, some of the bonds will break and the solid will melt into liquid, and when sufficient energy is supplied to liquid, all bonds, intermolecular forces, they may break so that the liquid will evaporate into vapor or gaseous phase. So gaseous state, it is having certain inherent characteristics which are listed in this current slide. So gaseous state exhibits expansibility, compressibility, diffusibility, pressure and effect of heat. So what is expansibility? It is limitless expansibility because little intermolecular attraction is there between the gas molecules, and thus it is able to expand to fill the entire vessel they are placed in. Compressibility, they can be easily compressed by application of pressure to movable piston fitted in the container. Diffusibility, they will diffuse rapidly through each other to form a homogeneous mixture. If you mix two gases, then they will get easily mixed homogeneously without requiring any extra force, which may be required if you mix other states, like if you mix solid with liquid or two immiscible liquids, then the diffusibility is not that great, which you can get with the gaseous state. Pressure, it exerts pressure on the walls of the container in all directions. Effect of heat, when a gas confined in a vessel is heated, the pressure will increase, and upon heating in vessel fitted with a piston, the volume of the gas will increase. So these are some basic characteristics of gaseous states. We are going to study gas laws. These gas laws are devised by certain scientists by observing the behavior of gases. First is Boyle's law. This is named after the scientist Robert Boyle. It states that at constant temperature, the pressure P of a gas varies inversely with its volume V. So denoted by the equation PV is equal to K, and where K is proportionality constant. Charles' law, named after scientist Jacques Charles, he stated that at constant pressure, the volume V of gas is directly proportional to its absolute temperature, that is T in Kelvin degrees. So V by T is equal to K, where again K refers to proportionality constant. Further, Gay-Lussac's law, this law states that the pressure of a given mass of a gas varies directly with the absolute temperature of the gas when the volume of gas is kept constant. So P is directly proportional to T. This also leads to the derivation, that is P1 by T1, ratio of pressure by temperature at certain set of conditions is equal to the ratio at another set of conditions. So the equation goes like this: P1 by T1 is equal to P2 upon T2. Then Avogadro's law, the volume of sample of gas is directly proportional to the number of moles in sample at constant temperature and pressure. This is very important, that you are specifying the conditions at constant temperature and pressure. So the equation goes like this: V is directly proportional to N. N is nothing but the number of moles of gases. So V1 upon N1 is equal to V2 upon N2, like we have specified for Gay-Lussac's law. So Avogadro's law, it is the relationship it's stated at constant temperature and pressure. Now, if you combine the gas laws, then it implies that the ratio PV upon T, this ratio always remains constant. Now it is stated with the help of equation that P1 V1 upon T1, that is pressure, volume, temperature of a gas at certain set of conditions, is equal to the PV upon T ratio at another set of conditions. So P1 V1 by T1 is equal to P2 V2 by T2, and this ratio is always constant. So given by R, that is nothing but the natural gas constant, and this R has value of 1.9872 calorie per degree per mole. Now students, this ratio PV upon T is equal to R, you can write it in this form also, PV is equal to nRT. So where N is referring to number of gram moles of a gas. If you are writing the equation for only 1 mole, then the equation will reduce to PV is equal to RT. But if you are writing it for n number of moles, the equation will be changing to PV is equal to nRT. Students, please understand this, that PV upon T, this ratio remains constant and it is nothing but R. So this means if you vary one of the parameter, either pressure, volume or temperature, then the remaining two parameters will adjust themselves so as to maintain this ratio constant equal to R. So this you should understand at this stage. Now PV is equal to nRT is nothing but the ideal gas law. These laws can be combined to form generalization, which is the behavior of gases, or it is also referred as equation of state. PV is equal to nRT, ideal gas law. It's also called as general gas equation or the equation of state of a hypothetical ideal gas. It is good approximation of behavior of many gases under certain set of conditions, although it has several limitations. So please do remember this ideal gas equation, PV is equal to nRT. That means the gases which obeys this equation, follows this equation, they are referred as ideal gases. But the gases which we work with, all those gases, they do not follow the ideal gas equation, and thus they are termed as real gases. Now we will see what difference is there between ideal and real gases. So an ideal gas is one which obeys gas laws or the gas equation PV is equal to RT at all pressure and temperatures. This is very important, that ideal gas is the one which obeys the law at all values of pressures and temperatures, but no gas is ideal. Almost all gases shows significant deviation from this ideal equation or ideal behavior. For example, gases like hydrogen, nitrogen and carbon dioxide, they fail to obey the ideal equation and thus termed as either non-ideal or real gases. Now let us understand what this ideality means. What exactly this ideal behavior means. Now this is explained with the help of kinetic molecular theory of gases, and this theory is all about certain assumptions made about the ideal behavior of gases. The assumptions goes like this: the gas molecules are point masses and do not occupy any volume. Or it can be stated in another way, gas is composed of particles called molecules and the volume occupied by these molecules is negligible as compared to the volume of gas. So this is first assumptions, where the gas molecules are considered as point masses, or you can say they do not exhibit any mass or weight and they do not occupy any volume, or the volume occupied by actual molecules is very much less compared to the total volume occupied by the gas. Second, the molecules are spherical, perfectly spheres, and intermolecular force of attraction is totally absent amongst them. Third, the particles exhibit continuous random motion owing to their kinetic energy. the average kinetic energy E is directly proportional to absolute temperature of gas. Equation for kinetic energy, E is equal to 3 by 2 RT. Fourth assumption, the collisions of molecules are perfectly elastic. That is, there is no net loss of speed after they colloid with one another or with the walls of container. Gas molecules are in continuous motion. So it is but obvious that during this random movement they are going to collide with one another or they can collide with the wall of the container. But this theory assumes that the collisions are perfectly elastic. Even after collision, the molecules are not going to lose their momentum or the velocity after collision. Fifth assumption, from above statements, the fundamental kinetic equation is derived, which is PV is equal to 1 by 3 nmc square, where P is pressure, V is volume occupied by n number of molecules of mass m having average velocity c. And the last assumption is the pressure of gas is caused by the hits recorded by molecules on the wall of container. The pressure which is exerted by the gas, it is nothing but the number of hits recorded by the molecules on the wall of container. So this is all about the assumptions of kinetic molecular theory for gases. Students, please remember these statements of kinetic molecular theory of gases, as they are going to be the differentiation points when we are going to compare behavior of ideal gas with real gas. So let's see what difference is there between these ideal and real gases. So ideal gas, the elastic collisions between these molecules or particles, whereas in case of real gases, non-elastic collisions. No intermolecular forces of attraction are there in case of ideal gas, but substantial intermolecular attraction forces, they are present in real gases. It does not really exist in environment and they are hypothetical gases. But real gases, they do exist in the environment. They does not obey gas laws at all conditions of pressure and temperature, and real gases obeys gas law at high temperature and low pressures only. This is very important point of differentiation, and you should remember this, that real gases obeys gas laws. That means ideal gas equation also obeyed by real gases, but only at high temperatures and low pressures. This we are going to study in detail with the help of one parameter, that is compressibility factor, that I'm going to cover soon. And the final point of differentiation is ideal gas obeys ideal gas equation, PV is equal to nRT. Real gases, they do not follow the equation PV is equal to nRT. So students, ideal gas equation is not able to explain the behavior of real gases, because real gases behavior deviates from the ideality. Now this is addressed by van der Waals equation. The equation was given by scientist van der Waals. In next lecture we are going to derive this van der Waals equation for real gases. So today I am concluding here. We will see the derivation for real gas equation in next lecture. Thank you for patient listening, and bye for now students. Happy learning.